Next, we are going to learn another scheduling algorithm, which is called round robin. So, round robin is widely used scheduling algorithm in real world. The basic concept is that each process gets a small unit of CPU time, which is also called time quantum. We use Q to represent this time quantum. Commonly, the value of Q will be set between 100 to 10 milliseconds. So after the time quantum elapses, a process is preemptive and added to the end of a ready queue. So no matter the process finish its execution or not, as long as the process finish its time quantum, the process will be moved out of the CPU and placed at the end of the ready queue. And then you may ask, so why round robin can be widely used in real world? Because it has the following properties. Assume n processes in ready queue and the time quantum is q. One good property is that round robin can guarantee each process gets 1 over n of a CPU time in chunks for at most q time units at once. The other good property is that no process weighs more than n minus 1 times q time units. So due to these two good properties, leading that round robin is very suitable for time sharing system. And actually, most of the operating system, include the one you used, they are time sharing systems. So that's why I'm saying that round robin is widely used in real world. And also in real world, how can we implement this special scheduling algorithm? Actually, it is quite simple. We just need to create a timer, and we use the timer to interrupt every quantum, and then to schedule next process. One quick comment I would like to mention is that if the value of Q is set too large, so we just change the round robin to first come, first serve scheduling algorithm. So we will further illustrate this point in the next coming slide. In this slide, we are going to show an example of a round robin with time quantum equals to 4. So in this example, we have three processes, which are P1, P2, and P3, with the CPU burst time 24, 3, 3 respectively. Again, we use Gantt chart to illustrate this example. We assume all these three processes are arriving at the system at the same time 0, and also with order P1, P2, P3. Then P1 is put onto the CPU first and to be executed for 4 time units because the time quantum is 4. Then P1 will be moved out of the CPU and placed at the end of the ready queue. Then the next process at the top of the ready queue, which is P2, will be put onto the CPU and get executed for 3 time units due to the total CPU burst time of P2 is 3, which is less than time quantum 4. Therefore, P2 will be terminated at time 7. Similarly, for process P3, it will be finished at time 10. Then only P1 will be left on the ready queue. However, the rest burst time of P1 makes P1 move between the CPU and the ready queue back and forth for 5 times. Then let's calculate the average waiting time for them. Since the waiting time of each process is a little bit complicated, so we are going to use the same trick as we used for priority scheduling algorithm. We use the turnaround time to subtract the fixed executing time to calculate the waiting time of each process. Then the waiting time for P1 will be 30 minus 0 minus 24 equals to 6. For P2, is 7 minus 0 minus 3 equals to 4. P3 is 10 minus 0 minus 3 equals to 7. Then the average waiting time is 6 plus 4 plus 7 divided by 3, which is equals to 5.67. So typically, the round-robin scheduling algorithm may introduce a higher average turnaround time or higher average waiting time compared to shortest job first, but it brings us a better response due to the two properties we just mentioned in the previous slide. From the above Gantt chart, so you can see that for each process, it only needs to wait for at most 8 time units, which will use n-1 times the time quantum. Here you can see that we use the 3 minus 1 times 4, which is equals to 8. Equals to 8. And then it can be put onto the CPU again. And also, each process can get 4 time units to be executed onto the CPU without any interruption. So that that is the advantage of a round-robin scheduling algorithm. It can provide a very good responsiveness. Then let's look at this example again. This time, if we set the time quantum to a large value, which is higher than or equal to 24, and leave other settings as the same, so we just reduce the round-robin scheduling algorithm to first come, first serve scheduling algorithm. So P1 will be finished at time 24, and P2 will be finished at time 27, then P3 will be finished at time 30. It is exactly the same as a first come, first serve scheduling algorithm. Since we cannot set the length of a time quantum to a very large value, how about we just set the value of a time quantum to a very small one? Actually, for doing that, it can bring extra overhead to the system as well. Usually, we just set the value of a Q to be large compared to context switch time. Then let's look at the figure down below as an example. In this example, the process time is 10. For the first case, we set the time quantum as 12. Then there is no context switch needed. For the second case, we halve the quantum to 6. Then one context switch will be introduced into the system. Then let's see the last case. If we set the time quantum to a very small value as 1, we need 9 context switch to finish the execution of this process. So you can imagine that if the context switch time is equal to the time quantum, half of the CPU usage will be used to do the context switch, which is just wasting 50% of CPU utilization. Therefore, normally we will set the value of Q to the range between 10 milliseconds to 100 milliseconds. And in real world, the practical time of context switch is less than 10 nanoseconds, so which is ignorable compared to the time quantum. So we won't bring too much overhead into the system when we use the round-robin scheduling algorithm. In the previous slide, we have mentioned that the time quantum cannot be set to very large. Otherwise, we just reduce the round-robin to first-come, first-serve scheduling algorithm. On the other hand, we cannot set the time quantum to a very small. Otherwise, we will bring too much overhead into the system due to the unignorable context switch, which can reduce the CPU utilization. Then the question is that how large the time quantum can be. The figure in this slide can give you a rough idea about how to set the time quantum. So in this figure, we show that how the average turnaround time can change with different time quantum under the given settings. So here we have 4 processes with a different CPU burst time, which are 6, 3, 1, 7 respectively. On the left side shows us that with different time quantum settings, we can get a different average turnaround time. According to this figure, we can get several observations. For example, this blue line does not show us a clear trend as we increase the length of the time quantum. It just fluctuated. In other words, increasing the length of a time quantum, it is not necessarily increase the average turnaround time. But from this figure, we can see that the average turnaround time can be improved if multiple processes can finish their next CPU burst time within a time quantum. For example, when we set the time quantum as 6 for process P1, P2, and P3, all these three processes can finish their execution within one time quantum. It can reduce the average turnaround time because the number of context switch can be reduced. As a rule of thumb, normally we just choose the time quantum that 80% of a CPU burst time should be shorter than the quantum time.